Welcome to another lesson in Business 12. This lesson is on neural networks. In this lesson, we'll discuss how a neural network is built from a non-technical point of view. This is a dog. More specifically, it's a picture of my dog, Pancho, and it's made up of over 1,000,000 pixels, or little dots on your screen, where each pixel represents a specific color and intensity. When your eye puts all these pixels together, your brain tells you that it's a dog. In a previous lesson, you learned that a neural network can be trained to recognize images of dogs, just like your brain can. And this neural network could be used to answer the question, is this photo of a dog? In order to answer that question, the neural network is constructed using layers of artificial neurons, where each layer plays a specific role in determining if the image in the photo is a dog or not. Let's define the different layers. The input layer of the network, which can be analogous to the retina in your eye, takes in specific inputs from the photo. If we assign one neuron to each pixel in the photo, registering the color and intensity of that pixel, then that would mean we have over 1,000,000 pixels in the input layer. Next, we can define the output layer of the network representing the answer to the dog question. Either yes, the image in the photo is a dog, or no, it's not. Finally, there will be a series of hidden layers that process the input data in successive steps to help the network determine if it is looking at a dog or not. You might be asking yourself, how do the layers in a neural network actually process the data in a photo to determine what it is? To get a better understanding, let's imagine a simpler example. Instead of analyzing a photo of a dog with over 1,000,000 pixels of various colors and intensities, let's consider a photo taken by a very special camera that can only take black and white photos that are 2 pixels by 2 pixels large. You can probably imagine the various photos that can be taken by this camera. Now, let's try to build a neural network that can recognize photos from this very special camera. In order to build our neural network, let's follow a simple, high-level, 3-step process. First, build the output layer, then the input layer, and finally the hidden layers in between. To begin building the output layer, we'll need to figure out what types of photos we want the neural network to recognize. In our previous example, the neural network was able to recognize photos of dogs. In this example, let's build the network to recognize specific patterns of 4-pixel photos. For example, solid colored photos, as well as vertical, diagonal, and horizontal lines. The output layer is built to answer the question, what kind of photo is this, based on the categories that we defined. And for each category, there is one neuron, for a total of 4 neurons in the output layer. When a photo is fed as input into the neural network, the network should respond by activating the neuron associated with the correct type of the photo. For example, if we provide a solid white photo, i.e. all 4 pixels are white, into the network should respond by activating the solid neuron, as indicated by the solid neuron turning white in the diagram. Similar activations should happen for photos of vertical lines, diagonal lines, and horizontal lines. Now that we have the output layer defined, let's build the input layer. To do this, let's remember that the input photos consist of 4 pixels. This means that we only need 4 neurons in the input layer, 1 neuron for each pixel. Let's further define which pixel is connected to which neuron by connecting them with white lines in the diagram. The white lines signify that the connected pixel will serve as direct input into the connected neuron. Now that each of the input pixels has been connected to a specific neuron, we will need to specify how the neurons in the input layer are activated, similar to how neurons in the output layer activate based on what the input photo is. Let's say that the first neuron is looking for a white pixel in the top left corner of the photo. The neuron activates when it finds a white pixel in that position, and we can indicate the activation by coloring the neuron white in the diagram. We can then place a reminder next to the first neuron so that we can remember what pattern the neuron is looking for, a white pixel in the top left corner of the photo. Let's now do the same thing for the remaining neurons in the layer. For clarity, let's assign the numbers 1 through 4 to the neurons in the input layer. And now the input layer is complete. Let's now move to the first hidden layer, where we create 4 more neurons numbered 5 through 8. Next, let's define what patterns in the photo will cause each neuron to activate. Building on the input layer, where each neuron represented a single pixel pattern, let's define the patterns for this first hidden layer based on 2 pixels in the photo as follows. 2 white pixels on the left of the photo, 2 white pixels on the right of the photo, 1 white pixel and 1 black pixel on the left of the photo, and finally 1 white pixel and 1 black pixel on the right of the photo. The next step is to connect the neurons in the input layer to those in the first hidden layer. We do this by constructing the pattern we are looking for in the hidden layer from corresponding neurons in the input layer. Let's look at an example. Neuron number 5 in hidden layer 1 is looking for a 2-pixel pattern, 2 white pixels on the left of the photo. We can build this pattern from neurons 1 and 4 in the input layer, which represent a white pixel in the top left and a white pixel in the bottom left of the photo respectively. While neurons 1 and 4 each represent an input from a single pixel, the 2 neurons combined represent the pattern that neuron 5 is looking for. We can then connect the outputs of neurons 1 and 4 as inputs into neuron 5 by drawing white lines as we did in the previous layer. Similarly, we can connect the outputs of neurons number 2 and 3 as inputs into neuron 6 to build the pattern it needs to be activated. Neuron number 7, however, is different. Notice that the pattern we are looking for in this neuron consists of 2 pixels on the left of the photo, a white pixel in the top left of the photo, and a black pixel in the bottom left. As before, we can use the output of neuron number 1 to get the white pixel needed at the top left of the pattern, connecting the 2 neurons with a white arrow to represent that connection. To complete the pattern for neuron number 7, however, we need to connect to a neuron representing a black pixel in the bottom left position of this photo. But if we review the neurons available to us in the input layer, we only have access to a white pixel in the bottom left position, represented by neuron number 4. So what do we do? If we think of black and white as opposites, then we may have a way. Using neuron number 4 as an input to neuron number 7, and recognizing that white and black are opposites, we can connect the 2 neurons. But instead of taking the output of neuron number 4, which activates when the bottom left pixel is white, we will use the opposite of neuron number 4 as the input, which activates when the bottom left pixel is black. We can then depict this graphically by connecting neuron number 4 and 7 with a black arrow. We can repeat the process for neuron number 8, which requires a white pixel in the top right position and a black pixel in the bottom right position, connecting neuron number 2 as a direct input and neuron number 3 as an opposite or negative input. Now we are done with hidden layer number 1 and can move on to building hidden layer number 2. Again, let's create 4 neurons, each looking for a specific pattern, this time a 4-pixel pattern as indicated. Using the same logic as in previous layers, we can connect neuron outputs from hidden layer number 1, or their opposites, to neurons in hidden layer number 2 to create the desired patterns. You may wish to pause the video at this point to review the connections between hidden layer number 1 and hidden layer number 2. Now we are ready to build the final hidden layer. In order to do so, let's review the patterns from hidden layer 2 to give us inspiration on what patterns to look for in this layer. Comparing the patterns in hidden layer 2 to the photos that the neural network is trying to recognize in the output layer, we can see that there is a direct correlation. But if you look a little bit closer, you might see that there are some photo patterns missing, and these patterns are what we need to complete the network. Hidden layer 3 includes all of the patterns necessary to fully recognize all of the desired photos. We then create neurons for each pattern to be recognized and connect them to the appropriate neurons, or their opposite, from the previous layer. The final step in this process is to connect the neurons from hidden layer 3 to the appropriate neurons in the output layer. Notice that a neuron in the output layer is activated if either a pattern, such as a solid 4-pixel white square, or its opposite, such as a solid 4-pixel black square, is activated. This is graphically represented by the 2 white arrows connecting neurons 13 and 14 to neuron 21, with the word OR included to indicate that only one of neurons 13 or 14 is required to activate neuron 21. The remainder of neurons are similarly connected to complete this network. And there you have it, a neural network that can recognize various 4-pixel photos. While this thought exercise doesn't give you a technical explanation of how a neural network is actually developed and trained, it does give you a basic exposure to some of the abstract steps used in creating a neural network itself. In the related concept exercise for this week, we'll walk through some examples of how this neural network processes input photos to answer the question, what kind of photo is this? Please review information in this video and do let me know if you have any questions that I can answer for you. Thanks for watching, and I hope that you found it interesting and educational.